Hey guys, Buildzoid here, and we're back with the topic of default motherboard settings not being very stable with high-end 13th gen, 14th gen Intel CPUs, because Intel has finally released a statement about this that actually has more details via email, and one of the publications that got the email is Hardware Lux. I unfortunately don't get emails from Intel. I only get really bad review sample CPUs. Uh, I wonder if that's why I don't get emails. Anyway, um, so let's read through the statements. Several motherboard manufacturers have released BIOS profiles labeled Intel Baseline Profile. However, these BIOS profiles are not the same as the Intel default settings recommendations that Intel has recently shared with its partners regarding instability issues reported on 13th and 14th gen K-SKU processors. So I guess that explains why the Gigabyte Intel Baseline Profile is so weird, because it didn't come from Intel, and in fact, it directly contradicts this table, as well as the old, public documentation. Um, so, yeah, and actually, since this statement, Gigabyte has actually removed the BIOSes with the Intel Baseline Profile. Asus hasn't, because, technically, the Asus one doesn't directly, there's nothing, yeah, I can't really. I'm not seeing what in the Intel baseline, the Asus Intel baseline profile, would be a direct, would be in conflict with this table or the old specifications. With Gigabyte, the issue is that their Intel baseline profile uses the 1.7 milliohm load line, which is meant for 35-watt CPUs on 125-watt CPUs, which leads to absolutely insane operating voltages. And also, if you read this public documentation, you'll notice that it says load line spec values should not be exceeded. If exceeded, power performance and reliability penalty are expected. So, yeah, I don't know what gave Gigabyte the idea that they're supposed to do this. And now that Intel has released this statement, basically reiterating that you really shouldn't be using more than 1.7 milliohms. You shouldn't be using more than 1.1 milliohms of load line for your, high-end CPUs. Gigabyte has taken the BIOSes down, whereas Asus just defaults to the 1.1 milliohm load line, which it's kind of against the Intel recommendations, but this is the it's still with it's not, the Asus configuration isn't above the maximum load line that Intel recommends. So technically in spec. And I don't see a reason that Asus would have to take it down. Anyway, let's keep going. So these Intel baseline profile BIOS settings appear to be based on power delivery guidance previously provided by Intel to manufacturers describing various power delivery options for 13th gen and 14th gen K-SKU processors based on motherboard capabilities. I'm assuming this guidance is very, very old guidance, from the early days of speccing 13th gen and 14th gen, because I have the version of this document that's for 13th gen only, as well as because this is 13th gen and 14th gen now, but originally this document was just 13th gen, and I don't remember there ever being a 1.7 milliohm load line spec for the high power draw CPUs. So I don't know, maybe very early on they had 1.7 milliohms for everything, and then that got revised to 1.1 for the high power draw stuff and 1.7 for the low power draw stuff. So I guess Gigabyte just use some really old design documents for their baseline profile, which explains why it's so weird. So anyway, Intel is not recommending motherboard manufacturers use the baseline power delivery settings on boards capable of higher values. Intel, please just make a frickin' spec instead of constantly making recommendations. But anyway, Intel's recommended Intel default settings are a combination of thermal and power delivery features along with a selection of possible power delivery profiles based on motherboard capabilities. Intel recommends customers to implement the highest power delivery profile compatible with each individual motherboard design as noted in the table below. So let's take a look at that table and go through all of the things your motherboard almost certainly doesn't. Well, if you have an MSI board, it might actually be pretty close. But Gigabyte and Asus, and especially Gigabyte, it's basically an inversion of this table. So let's go through, shall we? CEP, Both Asus and Gigabyte disable CEP by default. The reason for this is because they do not configure the ACDC load line according to how Intel would like it to be configured, and if you if you configure the ACDC load line the way Gigabyte and Asus do it, and then turn CEP on, you lose a bunch of performance because the way it's configured basically breaks CEP. So the workaround that the motherboard vendors came up with was, well, if we just don't use the current excursion protection, we can run AC and DC load lines that don't follow the Intel spec. Yay! Anyway, below that we have enhanced thermal velocity boost, and thermal velocity boost voltage optimizations. Gigabyte disables all of these by default. Asus, I think, runs some kind of mix of these. Anyway, this is the main reason why like Gigabyte motherboards have insanely high low load voltages, even compared to like Asus boards. Even though neither of them have any power limits, like it's pretty typical for my Z790 Aorus Extreme X. After a clear CMOS at low loads, the core voltage can easily go above 1.5 volts. And the reason this happens is because Gigabyte turns off the TVB functionality, and the way the TVB works on a 14900K is that you'll notice that the thermal velocity boost frequency is 6 gigahertz. And the performance all-core max turbo frequency is 5.6, not 5.7. So you might be wondering, why do these CPUs run at like 6 and 5.7? Well, that's because of how TVB works, because TVB works really strangely compared to basically any other boost algorithm that you would encounter on modern hardware. See, the way TVB works is that the CPU basically tries to go to 6 gigahertz right up until the temperature gets too high, and then it drops the frequency to like 5.9 or maybe 5.8. And the same thing happens for all-core, where it'll try to go to 5.7, and then as soon as it goes over the temperature threshold, it drops to 5.6. And so you'd think if you turn off TVB, you just lose the highest boost bins, but that's not what happens. What actually happens is turning off TVB disables the frequency drop when you exceed the TVB max temperature. So you go from a CPU that only goes up to 6 gigahertz with, I think, below 70 degrees or something. I'm not sure if Intel actually says at what temperature that 6 gigahertz is supposed to be like operational. But basically, if you turn TVB off, the CPU will try to do 6 gigahertz even at like 100 degrees Celsius. And the end result is very high operating voltages, because to compensate for, like, to hit a given frequency at a higher operating temperature, you typically need more voltage. So the CPU gets more voltage. And the same thing happens with the 5.7 gigahertz thermal velocity boost, where, you know, you try to run 5.7 gigahertz at like over the thermal velocity boost temperature threshold, and the CPU just needs more voltage to do that, so it just requests more voltage. Like, you'd think that turning off TVB would just disable the 6 gigahertz boost, but it doesn't. And actually, if you watched my video with like my experimental fix, you might have noticed that after I turned TVB on, the CPU doesn't do 6 gigahertz for single core Cinebench anymore. It maxes out at like 5.9, and that's because it's exceeding the thermal threshold for the 6 gigahertz thermal velocity boost. That's why that happens. And yeah, so Gigabyte doesn't have TVB like turned on at all by default. And Asus actually, I think Asus maybe might have a slightly tweaked configuration, because they don't have the insane low load voltages that Gigabyte has, but I don't think they drop the frequency like the Intel spec recommends, like the Intel spec would do, in my experience. So yeah, not entirely sure what's going on with the TVB on Asus boards, but on Gigabyte it's just straight up disabled. Then we have the ICC Max Unlimited bit. This is enabled, of course, because the Intel recommendations say it should be disabled, so of course it's enabled. Basically, this means you don't have a current limit. If the ICC Max Unlimited bit is turned on, it doesn't matter what current limits you punch into the ICC Max setting in your BIOS, the CPU will just completely ignore it, and you do not have a current limit. By default, this is turned on. On Gigabyte, if your ICC Max is set to auto in the CPU configuration, like advanced CPU settings, that is ICC Max Unlimited on. On Asus, you actually have like a separate setting that you need to disable. in order to get your current limit enabled. I'm not really a fan of how this works, like, kind of weirdly backwards, right? Like, ICC Max Unlimited is, it makes sense if you read what the setting is called, but yeah, like, you need to turn that on. Off, to get your, like, current limit enabled. So, anyway, then we have TJ Max offset, that's at 0. I don't think I've ever seen a motherboard set this above 0, so yeah. So that's the thermal limit, right? And Intel says TJ Max is supposed to be 100C, and basically if your CPU isn't thermal throttling at 100 degrees, then yeah, you have a TJ Max offset, but I've never encountered that. C states typically are enabled. I don't think, like, yeah, I don't think that's a very usual thing for motherboard vendors to, like, disable the C states. I don't think I've ever seen that. And then we have AC and DC load line settings. AC says varies, and we're going to get into this. DC load line says must match the AC load line. Yeah, most motherboards don't do that. For example, here's my Gigabyte Z790 Aorus Extreme. I literally just cleared the CMOS on it. Let's see what the ACDC load line is. You can check this with hardware info. So if you want to check your motherboard, you just download hardware info. You launch this full, like, system thingy. Anyway, and then you just click on your CPU, and here you can actually check things like, hey, is my ICC Max Unlimited? Yes, it is. And you can also check the load line, and you'll notice that, AC is 0.4 milliohms, and DC is 0.9 milliohms. Those are two different values, not in line with the Intel recommendations. And this is one thing and the reason the boards do this is because the DC load line, if we read the spec again, right? So, where is it? Right, so AC-DC load line BIOS programming directly affects the operating voltages, which is the AC load line. So changing the AC load line setting changes the operating voltages of the CPU. The motherboard vendors like to set the AC load line too low, which basically undervolts the CPU, which is why if you buy a brand new 14900K and you lose the silicon lottery, it'll crash on auto settings, because the AC load line is too low. And it doesn't happen on all CPUs, because even though, like, you might think that the SP rating is like an absolute indicator of, like, undervolting headroom and overclocking headroom, it's really not. You can get, like, if you had, like, a bunch of CPUs with the exact same SP rating, you will find that they actually have different amounts of undervoltage headroom before they start getting unstable. So even if you had, like, 10 CPUs, all of them are SP91 or SP95, so SP rating, right? Which is basically, that's like ASUS's name for, I think it's like silicon prediction or something. Basically, ASUS takes the vid table, does some math with it, and converts it into a number that indicates, like, rough silicon quality. But the problem is the Intel vid table from the factory, it is applied to, like, each CPU gets its own vid table, but how much headroom there is below the vid table for the CPU to maintain operation actually varies by CPU. So you can get, like, you can get some CPUs with really good vid tables with, like, no undervolting headroom, and you can get some CPUs with very bad vid tables with tons of undervolting headroom. And you can also get CPUs with very bad vid tables and no undervolting headroom. And so if the motherboard has the AC load line set a little bit too low, CPUs that don't have any undervolting headroom, yeah, they crash. And CPUs that have undervolting headroom, they run better, right? Because they're running at lower voltage, so they're hitting the thermal limit less, they're hitting the power limit less, and that's why the motherboard vendors like to set the AC load line to things that aren't universally stable, because it boosts benchmark scores when it doesn't cause blue screens, as well as crashing. So Intel evidently isn't a big fan of that. Also, because of the way the AC and DC load lines are configured, CEP is CEP breaks, so the motherboard vendors turn off CEP. CEP is the thing is, like, CEP's side effect is that it basically prevents undervolting. But you'll notice that the name is current excursion protection. This is probably meant to, like, protect the CPU from excessive electromigration. probably a good idea to keep that turned on if you value your silicon surviving a long time. But then it's not compatible with messed up ACDC load lines, so yeah, like Gigabyte turns it off, Asus turns it off. I don't know what MSI and ASRock do. Anyway, so yeah, I imagine like with that I think is going to be the biggest change going forward is like the ACDC load lines. Like we're not going to get this anymore, where it's like 0.4 and 0.9, and because yeah, like that's not supported officially by Intel, or like they're not recommending it. And if we read the notes over here, AC load line must match the design target. This is the other issue. So where the undervolt actually sort of comes from, because you'll notice like, okay, so AC load line affects the operating voltage. Oh, and I didn't actually read through the whole thing. And power measurements are set by the DC load line. So if you mess with the DC load line, that'll mess up the power readings. If you mess with the AC load line, that messes up the operating voltage, right? So what the boards basically do, so like Gigabyte, basically, when they set this to 0.4 and 0.9, the 0.9 is so that the power readings are actually relatively accurate, as far as I can tell. The power readings on this motherboard make sense when compared to the power readings from the VRM with the 0.9 milliohm load line. And if I set it to 0.4, the power readings actually get like kind of too low. So what Gigabyte basically has done here is the default V-droop on the motherboard, so like the design of the motherboard, is tuned for, I think, 0.9 or something close to 0.9. So the DC load line is at 0.9 so that the power measurements are accurate, but they set the AC load line below what the motherboard is actually running so that you get that, like, undervolt and instability if you're unlucky enough, right? So yeah, I'm sure Intel is thrilled about their load line settings being used like this, because yeah, you're not really you're not supposed to do that anyway. But I still have the issue with this, where Intel says AC load line must match the design target with a maximum value of 1.1 milliohms. So this I've never seen a motherboard actually exceed until the Gigabyte baseline profile came along. That was the first time I've seen a motherboard go over like 1.7 milliohms on the load lines. DC load line must be equal to AC load line, which makes sense if you think about it, and honestly makes me, because like here's the thing, if your VRM is configured in such a way that, you know, in order to get accurate power measurements, so like your VRM has 0.9 milliohms of load line, so the DC load line is set to 0.9 so that the power measurements are accurate, right? And then you set the AC load line to anything other than 0.9, well, now the AC load line is either above what the VRM is configured to or less than what the VRM is configured to. And that's not good, as you can probably guess. And so the thing is, so Gigabyte uses 0.4 and 0.9. On some BIOSes in the past, Gigabyte actually used like 0.6. Funnily enough, I've been made aware that I kind of suspected this, but I didn't really bother to investigate. But Gigabyte's been basically changing the AC load line value up and down with like BIOS updates, and mostly down. I guess they've been progressively lowering it more and more as they were like, well, you know, if we lower it another 0.1, it'll give us higher benchmark scores, which is not great. Asus typically uses 0.55 and 1.1 for the AC and DC load line settings, which also, like, you know, they're not matched. So that's also just like an undervolt right out of the box, because if the DC load line is matched to the VRM configuration and the AC load line is less than that, well, the AC load line doesn't match the VRM configuration, does it? Which really makes me wonder, why are these even separate settings, Intel? Because why would you ever want them not to be matched? Other than if you're trying to undervolt the CPU. And there's better ways of doing that. You literally have like voltage offsets. Actually, I guess if you wanted like a dynamic undervolt that gets progressively bigger at high load, then being able to intentionally set the AC load line too low makes sense. But anyway, so for the default configuration to maintain stability, you shouldn't have your AC load line at anything other than the DC load line. because that's not stable, depending on the CPU. Anyway, the thing I don't like with these notes, though, is lower values are possible if they match the board design and voltage regulator capabilities. Voltage regulator and BIOS load line values must match. Yeah, that currently isn't the case, right? That's where you get that undervolt. But the issue I have with lower values are possible if they match the board design is who is going to make sure that the load line settings in the BIOS actually match the board that comes with that BIOS, right? That's my main issue with Intel's approach to the load lines here, where it's like, does Intel want to play the load line police? Because I don't trust the motherboard vendors to set this themselves correctly, because they're evidently not capable of doing that based on past evidence, right? Like just the fact that Gigabyte has been actually, you know what? I'm going to pull up the fact that like they've been changing the AC load lines and DC load lines with BIOS updates. So here we go. Right? So this is a response to a tweet that I made about like suspecting that Gigabyte does this, and yeah, like optimization for improved VRM and processor overclocking thermal performance, CPU load line adjustments. Why are they changing this? Because if you look at the Intel documentation, right, the public Intel documentation, load line ACDC should be measured by the VRTT tool. Intel gives the motherboard vendors a voltage regulator test tool and program accordingly via BIOS load line override setup options, right? So Gigabyte, when they were developing their Z790 and Z690 motherboards, I think this is for a Z690 board. Yeah. Oh, wait, no, wrong tweet. Yeah, this is for a Z690 board. Like, when they were developing these Z690 motherboards, Intel would have given them this tool. They were supposed to use the tool to measure the AC/DC load line of their motherboard, and then they were supposed to punch in the numbers the tool gave them into the BIOS. Unless the motherboard, changed over time, they shouldn't be changing the load line settings, right? When they first designed the motherboard, like, unless they reprogrammed the voltage regulator, but as far as I know, you can't really do, well, I guess you could do that, if they tweaked the, because yeah, you could just adjust the load line configuration the same way like the BIOS gives you VRM load line settings. They could have just used that to change it after the fact, but like, did they not use the tool properly the first time? Did they not have the tool? Did they not understand how to use it? Right? So my whole issue with this is like, third parties, like the only people who have access to this tool is Intel and the motherboard vendors. And Intel seems willing to trust the motherboard vendors to actually use the tool correctly, which based on current evidence, I would say is not happening. And I don't know why that would change. Because the thing is, like, if you buy a Gigabyte motherboard or an Asus motherboard or an MSI motherboard, and you check your AC/DC load line settings, right? Like you open up hardware info and assuming that they change this to be like 0.9, 0.9 or something instead of the current 0.4 and 0.9, which is very clearly against Intel's recommendations already. Like, so let's say they stop changing them to two different values and actually use one value for both. But how do you know that that value is correct? Unless you have access to the VRTT, right? Unless you have the test tool, you don't know if your motherboard has its AC/DC load line set correctly. Because, like, so Intel would basically have to police this, right? Because even reviewers don't have access to this tool. Like, nobody does. Like, if you're not a motherboard manufacturer or Intel, you don't have access to the tool. So how do you know that the load line is set correctly out of the box? You can't. So basically, Intel would have to go, take every single Z690, Z790 motherboard, measure, and at this point, like, if Intel's going to do that anyway, right, like, take the motherboards, measure the load lines on them, and then go tell the motherboard vendors, hey, you can't set, you're setting it wrong. Like, why is this even customizable? Right? Like, why would you let them set this themselves when they're evidently not going to follow instructions? Also, I guess, so this is one thing I was wondering about, was like when the AC load line here says same as DCLL, right? Like, I figured because it's in the maximum column, that it just means AC load line must not be higher than DCLL. But evidently what Intel meant by that is, no, it has to be exactly the same as DCLL, regardless of what DCLL actually is. Yeah, I guess I wasn't the only person who saw that this was in the maximum column and went like, well, that means it's fine if we set it lower than that, right? Yeah, like I still don't think it is okay to have this being configured by the motherboard vendors, because like, and the other issue is like right here, right? It says a superior board design with a shallower AC load line can improve on power performance and thermals compared to boards designed for a point of reference impedance. And the issue I have with this is like, yeah, but designing a better board is expensive. Intentionally setting the AC load line wrong is cheap. In fact, it's free, basically. Well, not literally free, right? Somebody needs to go in and actually like set the values in the BIOS, but yeah, like it's much cheaper than actually designing a better board. So, and also there's like a lower limit to what the AC load line could ever be, because the CPU socket has like a fixed amount of impedance that you can't get rid of. It's just there, right? Like if you have a CPU socket, there is a minimum value that your AC load line can be, and your DC load line can be. Which is why I'm not a fan of the fact that there's like a minimum of 0, because like that's physically impossible unless the CPU socket somehow disappears. Right, and this is specifically for the socketed CPUs. And even if you had a BGA, the BGA doesn't have 0 resistance and 0 inductance. It's a lot lower than a CPU socket, but it's not 0. And then, of course, you have the substrate of the CPU itself. That has some resistance and inductance. Because the voltage regulator actually monitors the output voltage at the die, right? Like it has the voltage measurement point is the sense points that are provided by Intel, and those are connected like right before the silicon, or like at the silicon, or maybe even somewhere inside the silicon. I don't know how Intel wires in the sense points, yeah, so like this being 0, I feel like this should have a minimum value of whatever the like CPU substrate and socket load line work out to be on their own, as a minimum value, right? But anyway, so back to this. So yeah, I'm still not a fan of like Intel has to basically police the load lines if they're gonna, and at that point they may as well just configure them themselves. So I am not a fan of this being like, oh, the motherboard vendors can set this, because like who's going to prove that the motherboard vendors are setting it correctly? Right? Like it's relatively easy for somebody like me to go into the BIOS and go like, well, TVB is turned off, CEP is turned off, the ICC Max is turned on, the power limits are set sky high. Like I can check all of that, but I have no way of verifying that, you know, the ACDC load line settings are set according to what the VRTT tool would actually want, because I don't have that tool, right? And like, yeah, you might be able to get the load line setting out of the voltage regulator, but how do you know that the motherboard vendor isn't setting that below what it's supposed to be? Right? Also, I guess this means that my experimental fix is not following the Intel spec, because yeah, I obviously don't have a VRTT tool, but my thought process on like the whole like set the load line to extreme and then try to set the AC and DC load lines to match that, which is really low, was, well, even if the extreme LLC might be too high, like that might be too little V-droop for the design of, like for the physical properties of the motherboard, at least it brings the average voltages way down compared to any other configuration I tested. So I personally would think, I'm not sure how stable it's going to be, but from like from a long term, like from a longevity perspective, it is better to have a CPU averaging 1.45 volts with some kind of high transient spikes, because also the biggest transient spikes you're going to get are going to be at high load, not low load. So, the fact that at low load you're at like 1.45 volts, that's not really a big deal. You're not going to have like a 200 millivolt overshoot when pulling 60 amps, right? So I'm not too concerned if the average voltage, like if you have 1.45 volts at low load and then there's like a transient spike upwards from that, because it's not going to get, like the voltage isn't going to get that high. And at high load, you're going to have 1.2 volts, and the or like 1.3 to 1.2 volts, and then like sure you're going to have a bigger transient overshoot, but you're starting at a lower voltage, so it's still not really going to be a concern. The thing is, like with my configuration, the undershoot might be too low, though I kind of suspect CEP can deal with that. I think I'm not sure. Maybe it can't. So I'm kind of like misusing CEP in that way. With my like experimental fix, but where was I going with this? The alternative, if you use like standard AC load line or like higher V droop on the VRM and then set the AC load line to like 0.9 or something, is your average voltage for low loads ends up significantly higher even if you have TVB turned on. And I would much rather have a CPU that runs between, 1.45 volts and 1.2 volts with more overshoot than a CPU that runs between 1.55 volts and 1.2 volts, because the max load, like the high load voltage, isn't really limited by the load line settings, it's limited by the thermals, right? So if you have a cooling system that can cool 1.2 volts, it's going to be cooling 1.2 volts regardless of what your AC load line settings are, right? Unless you... Well, no, it's always going to end up at 1.2 volts, because if you set the power limit, it's going to do the same thing. You're just going to, like... Because your cooling system basically acts like a power limit. If your cooling system can dissipate 300 watts, the CPU will output 300 watts, right? And because of how like frequency does increase, like frequency affects power consumption, but not as much as voltage. So if you're at 5 gigahertz and 1.2 volts, your power consumption is basically the same as if you're at 5.2 gigahertz and 1.2 volts. So that basically means that, yeah, like if you run, like, so when I was tuning the ACDC load line settings for my experimental fix, my goal was to just get the average voltages as low as possible, because that I think is better for the CPU than having a low load voltage of in excess of 1.55 volts and then still having the exact same overshoot at high load, right? Like the overshoot at like 100% load is still going to be the same. That's not really going to change very much. The undershoot might get better, but that's only a concern from like a stability perspective, and as far as I can tell, CEP seems to deal with that. But maybe it doesn't. Anyway, so, so evidently, like, my experimental fix also isn't, like, doing this correctly, because I obviously don't have a VRTT, so I don't know what I'm supposed, like, I don't know what the load line settings are supposed to be. Anyway, or actually, I guess you could also get that from like the design documents, but basically I don't have access to the things that would tell me like, hey, this is the actual correct ACDC load line configuration for this motherboard. Anyway, so yeah, well, it's nice to have some clarity on that. Yes, AC and DC load line should in fact be exactly the same value, not just AC load line can't be higher than DC load line. That's nice, I guess. Now let's go through the actual power limit. So first of all, ICC Max, because both Gigabyte and Asus set the ICC Max unlimited bit, the ICC Max value itself is just completely irrelevant, because the CPU is going to ignore it even if you set that, unless you disable the unlimited bit. But anyway, Intel says that even for the extreme configuration, never exceed 400 amps. Cool. ICC Max app, 320 amps. I've never seen this actually be a setting in the BIOS, so I do not know where you would set that. Anyway, it's not the VRM current limit, by the way. The ICC Max app thing is. That's a separate value that's not really talked about because it's not really relevant for most high-end Z790 motherboards, or even like $200 Z790 motherboards. The VRM on those boards is perfectly capable of outputting 400 amps. The power plane is going to get really, really hot, but if you have airflow over it, it'll do it. So Yeah, like you're not really like the current limit of the VRM isn't really a concern. It's more like a thermal limit that you have to worry about with the VRM. Like you're not going to have a scenario where on a like $200 Z790 board, uh, you start up an all-core workload and the VRM just instantly like gets instantly overloaded and up and dies. That's not going to happen. You're going to have plenty of time before the VRM gets to a temperature where it like has to thermal throttle. And also, cooling 320 amps going into a 14th gen or 13th gen is extremely difficult. I can basically guarantee you're going to run out of cooling before the VRM has an issue. Um, yeah. Like, unless you have like a water chiller or something, you are going to run out of CPU cooling before the VRM current limit becomes a concern. So, the ICC Max underscore app, this is, I think, more for like OEMs like Dell and HP, where, you know, they're trying to keep the motherboard cost low, instead of enthusiast Z790 boards where the board will actually probably destroy your CPU before the board gets damaged if you let it do that. Like, you know, if you wanted to do that. So anyway, then for the power limits, PL1 and PL2, 253 watts for the extreme config. And the performance configuration is supposed to be 125 watt PL1. Now, I find this, like, I guess it makes sense because, like, the 14900K is like, where is it? Advertised as a 125 watt CPU. But the problem is, like, you can hit that 125 watts with just 4 cores loaded, or even 2, depending on how heavy the workload is. So the thing with this like performance configuration is I think there are games out there where you could actually hit 125 watt PL1 on a 14900K or 13900K. I think it's more likely that it'll happen on a 14900K just because the voltages tend to be higher. And so the performance profile would actually, even in like gaming, would potentially be quite a bit slower than the extreme profile. Because yeah, hitting that 125 watt PL1 is not hard. But at the same time, like I mentioned earlier, like, you know, even a $200 Z790 motherboard will quite happily put 300 amps, 400 amps through your CPU. There's no reason for any Z790 motherboards that I'm aware of to actually use this configuration, right? Because Intel, like in the statement, they're like, yeah, Intel's recommended Intel default settings are a combination of thermal and power delivery features along with a selection of possible power delivery profiles based on motherboard capabilities. So basically, if you have like a $200 Z790 motherboard, it should use the extreme profile. Because they're like, you know, like the performance profile is for crappy motherboards, basically, is what it is. So I don't think we're going to see any boards use this. Also, I don't think this would change stability because basically if you're going to crash, you're going to crash probably, well, no, because like you might be in scenarios where you might just crash on before the PL2 runs out. Anyway, PL4, I don't even know where that is in the BIOS. I've never seen it. That's set for 380 watts on both. That's like a peak power limit. Honestly, I think that's mostly handled by ICC Max already, because ICC Max, like if you set this to 400 amps, like that basically acts like an average power limit of 320 watts-ish. 320, yeah, something around like 320 to 350 watts. Anyway, so that's for the regular K SKUs, and then for the KS SKUs, the extreme profile goes 400, same, 320, 320, 320, 550. What I find confusing about this is this would imply that the KS chips have like more reliable silicon, which, I mean, that's not impossible. That the KS chips would have like more robust silicon. I just find it kind of hard to believe that Intel would be binning that hard for that. Because that seems like a awkward like that seems like an awkward thing to try select CPUs for, right? Like intentionally finding the chips that are gonna like handle 320 watts of power draw better than the other chips like that. It seems a bit weird to me. Or it's maybe just to not nerf them as much in benchmarks. Also interesting that the performance configuration for the supposedly 150-watt CPUs is still 253 PL1. Yeah, so like personally, looking at these guidelines, I would like use the KS configuration on everything. Um, and I'm far more concerned about the fact that like most motherboards, they disable CEP, they do weird things with the TVP or completely disable the TVB. They enable the unlimited ICC Max bit. Actually, they don't do anything to C states, and then the ACDC load line are just kind of whatever the motherboard vendor felt like would get them better scores and benchmarks. Right, that like the basically the top half of this table I find much more concerning. Oh, I also the ICC Max. I would not, like Intel very clearly says never exceed 400 amps. I'm going to assume that's because it's a reliability concern for the CPUs. And by reliability, I don't mean like crashing. I mean like the CPU might degrade rapidly if you don't have a current limit. So yeah, so that's the Intel recommendations. Also, this video is way too long again. How do I keep doing this? But yeah. So, like, my only complaint is like, who's gonna enforce the load line settings? I get like I'm hoping Intel like just goes and like checks the motherboards and tells the board vendors like, look, you can't. Your load line settings are not correct. Fix them, please. Because like it just doesn't make sense to me that you would let them change this, right? Especially like, oh well. So yeah, and I think I mean that's my thoughts on this. So I'm not sure if like, because like the thing is, there's also like from a like I think what this table basically covers, if you have a brand new CPU and it's not stable, and you like follow the guidance of this table, and it's still not stable, which admittedly is really difficult when you have no way to check what the correct load line for your motherboard is. But if you follow the guidance of this table, I'm going to assume that like you should, at the very minimum, be able to stabilize a brand new CPU. The thing is, there's also like talks of people having CPUs that were running for months and months and months, and originally they were stable and now they're unstable. But that could be because of like sketchy BIOS updates by the motherboard vendors, pushing the AC load line progressively lower every few months or something. So, like when you first built the system on the brand new BIOS, the AC load line was set higher than it is on the very latest BIOS. And that's why, like, so basically it's like, oh, I updated the BIOS and now my CPU is unstable. And it's not because your CPU degraded, it's because the motherboard vendor has progressively undervolted your CPU more and more with the, with each BIOS update. Or like the latest BIOS update just runs you get the idea. Like it's actually just running less voltage, which might be why you're unstable instead of like the CPU actually degrading. But then there's also, like, it is still possible that some CPUs did degrade, and I imagine if you follow these like the recommendations from Intel over here, they won't fix anything, I don't think, if your CPU is degraded. Now the thing is, I don't think, like, because most motherboards don't use CEP, they don't have the TVB configured the way it should be. The ICC Max is disabled, right? Like the ICC Max Unlimited is turned on, so the ICC Max is disabled. Because of that, I think it's really hard to say that like Intel messed up their like reliability testing, because like nobody was using the current protection, like the current excursion protection. Yeah, that's disabled. The ICC Max, that's also disabled. So it's like, well, is the CPU degrading because Intel is pushing the CPUs too hard? Or is the CPU degrading because there's literally no safety features turned on whatsoever, right? TVB is not being configured correctly. CEP is off. ICC Max is off. Like, all of Intel's, like, degradation prevention functionality is off. And it's just like, And the funny thing is, a lot of people might think, yeah, so the degradation protection is off, and then it's overvolting the CPU. No, it isn't. Well, I guess at low load, it might be. So like single core load, if your TVB isn't correctly configured, you get a lot of voltage. But at 100% load, the voltage actually doesn't really change because you're hitting the thermal limit. And the board vendors don't really play with that, luckily. So my suspicion for a while now has been that actually most of the degradation with these CPUs happens either right at the start of a workload. So like when when the CPU starts working on something heavy and you get a huge current spike as it hasn't hit the thermal limit yet, right? Because as soon as it hits the thermal limit, it doesn't matter if your ICC Max is unlimited, it's going to throttle itself back. Though I guess depending on how fast the ICC, like you could have some very quick current draw spikes even as the CPU is thermal throttling. But the other thing is you could also have degradation at like partial load because your low load voltages are sky high because TVB is turned off, right? So yeah. So I think from a like brand new CPU not being stable, I think this table should address that. Old CPU not being stable, this table might address that, but from like CPU might have been degrading. Yeah, I don't think this is going to fix that, but hopefully Intel's just going to replace your CPU if it's like degraded due to running with, no current limits, no thermal velocity, like thermal velocity boost misconfigured and all of that. So yeah. The thing I'm wondering about is like, well, anyway, I guess we'll find out. But at a bare minimum, it's like with this table, it's now very clear what the motherboard vendors are like doing wrong, and I still think the main focus is the AC and DC load lines. Like that, I think is especially responsible for any case of like I buy a new CPU, I put it in my new motherboard, and then I try to run a workload and it just crashes. It's probably because your AC and DC load line are not set correctly. Yeah, it's good to have some official clarification because honestly, I didn't think this was a problem. That like I didn't think this was a problem what Gigabyte is doing here, because if you read the documentation, the public documentation from Intel, it says maximum, right? It says same as DCLL. I think. Like I don't I'm gonna assume that the motherboard vendors probably have better documentation than the general public, but I think like it would have made more sense that this same as DCLL would be everywhere, instead of just in the maximum column. Because as it is, it kind of looks like, oh, ACLL cannot exceed DCLL. It doesn't look like, oh, ACLL has to be the same as DCLL, which is what Intel is now saying with this table. So, though maybe it changed, right? Like, I don't know. Maybe it used to be my original, maybe it was okay that you set it too low, but I kind of doubt that because like it breaks CEP when you do that, and it's always broken CEP when you do that. So anyway, yeah, that'll be actually it for this video at this point. So this should fix I think this should probably fix the instability on new CPUs. On old CPUs that may or may not have degraded, I'm not sure. But considering that most motherboards, like I've already said everything I have to say, let's not go over that again. So hopefully you found this video interesting, if not particularly useful. And thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with the channel, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's links to all of that down in the description. It'd be much appreciated if you check them out. And that's it for the video, so thank you for watching, and goodbye.